Here's another interesting paradox. It's related to the no-show paradox and other paradoxes in which there's a failure of monotonicity, although the phenomena is a bit different. This is the so-called multiple districts paradox. The idea is that we have our society, and we're holding an election. And what we do is we divide our voters up into districts or regions. So we have, let's say, 3 different districts. And we have the voters rank all of the candidates and submit their ballots as usual. And we run an election. We use some voting method to determine the winner. And it turns out that in each of the districts, candidate C, the same candidate, wins all of the districts. Naturally, we would like to say that that candidate should be declared the winner. However, when we run the election, ignoring the districts, so we have everybody rank the candidates exactly as they did when the electorate was divided up into districts. So the rankings are exactly the same. There's no new voters. We haven't removed or added any voters. But now when we run the election, we see that candidate C is not declared the winner. And that's the multiple districts paradox. And this certainly is counterintuitive because we haven't changed any of the rankings. All we've done seemingly is just counted the ballots, aggregated the ballots in a different order, in a different way. Now, there are a number of different voting methods that are susceptible to the multiple districts paradox. In particular, plurality with runoff is a famous example. But rather than using plurality with runoff, I want to look at a newer voting method. It's slightly more complex, but it's the voting method majority judgment, which was popularized and extensively studied by Belinsky and Liricki. Now, the way this method works is there's a set of grades, and each voter can assign any grade he or she wants to a candidate. Then we look at the candidates and we determine that candidate's median grade, and the candidate with the highest median grade is declared the winner. Now, if 2 candidates have the exact same median grade, we need some tie-breaking rule to determine who's the winner. Belinsky and Liricki proposed an interesting tie-breaking rule, which we'll use rather than describing it in the abstract. We'll look at a concrete example on the next slide. All right, so here's the situation. We're going to have 3 regions, and we're going to see that in all of these regions, candidate X is declared the winner. So here's our first region. We have 2 candidates, X and Y. And what I'm recording here is how many of each of the grades the candidate received. So candidate X received 21 A's, 31 B's, 48 C's, and 1 D. Whereas candidate Y received 40 A's, 11 B's, 48 C's, and 2 D's. All right, so now we want to calculate the median grades for each of X and Y. Let's start with X. The way we're going to do it is we're going to match up the highest grades with the lowest grades, and we're going to iteratively remove those until we have we're left with the median grade. So we match 1 D grade with 1 of the A grades, so we're left with 20 A grades. Then 20 of the A grades are matched with 20 of the C grades, so we're left with 28 C grades. And finally, these 28 C grades match with 28 of the B grades, and we're left with 3 B grades. And so X's median grade is a B. What about candidate Y? Well, 2 of the D grades is matched with 38 of the A grades. 38 of the A grades is matched with 38 of the C grades. That leaves us with 10 C grades. And then these 10 C grades are matched with 11 of the B grades. So we're left with 1 B grade. So candidate Y, the median grade is a B. There's a tie, so now we need to decide what to do. The way the tie-breaking rule works is that you go back to the original set of grades and you remove 1 of the median grades from each of the candidates X and Y, and you do this whole process over again. You calculate the new median grade. So we go back to the original set of grades, and we remove 1 of the median grades, which was a B, from each of the candidates. So now we have 30 B grades and 10 B grades for candidate Y. And then we do the whole process over again. So the 1 matches with 1 of the A grades, so we have 20 A grades. 20 matches with 20 of the C grades, so we have 28 C grades. And finally, the 28 matches with 28 of the B grades, so X is left with 2 B grades. So X's median grade is a B. What about candidate Y? Well, again, we do the same process. So 2 matches with 2 A grades, so we have 38 A grades. The 38 matches with the 48 C grades. So we're left with 10 C grades. And we see now that we have 10 C grades and 10 B grades. So they match up exactly. So what do? Well, the idea is we say, well, 9 of the B grades matches up with 9 of the C grades. And so candidate Y is left with 2 median grades, B and C. There's 2 grades in the middle, and there's nothing, we can't average these grades, so there's nothing in between. What we do, the procedure tells us that you always take the lowest median grade in that case. So Y's median grade is a C. So X is declared the winner. We can do the exact same procedure to see in region 2 that X will be declared the winner here. You're going to have to apply the tie-breaking rule more than once. You keep applying the tie-breaking rule until you determine the winner. Similarly, in region 3, we see that candidate X will win. I encourage you all to pause the video and make sure that my calculations are correct. You should double check and really make sure that candidate X is declared the winner in each of these regions. All right, now for the multiple districts paradox. What we do is we merge all of these regions. So we take region 1, 2, and 3 and we merge them together. What does that mean? Well, that means candidate X has a total of 21 plus 1 plus 0, 22 A grades. Whereas candidate Y has 40 plus 1 plus 0, 41 A grades. So the numbers down here reflect the overall grades in the entire society. And now what we need to do is go through and calculate which of X and Y should be declared the winner. All right, so to do that, we match these 22 A grades with 22 of the D grades. That leaves us with 60 D grades. 60 of the D grades gets matched with 60 of the B grades, and that's going to leave us with 57 B grades. And then finally, the 57 B grades is going to match with 57 of the C grades, so that should leave us with 25 C grades. So X's median grade is a C. What about candidate Y? Well, 41 of the A is going to match with 41 of the D, so that'll leave us with 33 D grades. 33 of the D grades is going to match with 33 of the B grades, which will leave us with 71 B grades. And then 71 of the B grades is going to match with 71 of the C grades, which will leave us with 13 C grades. So Y's median grade is a C. So again, they tie, so what do we have to do? We have to go back to the original data and remove a number of, well, we remove one of the median grades, C, and we do the process over. Obviously, since there's 13 C grades left and 25 C grades left, we're going to have to do this a number of times. So why don't we just go ahead and jump ahead and remove 13 C grades from each of X and Y. So if we do that, if we remove 13 C grades from candidate X, we end up with 69 C grades. Yes, 69 C grades. And if we remove 13 C grades from candidate Y, we end up with 71 C grades. All right, so let's calculate the median grades for each of the candidates again. So the 22 matches with 22 here. We're left with 60. 60 matches with 117 here. So we're left with 57. 57 matches with 57 grades here. So we're left with 12 C grades. So X's median grade is a C. What about candidate Y? Well, 41 matches with 41D, so we're left with 33. So again, the 33 matches with 33B, so we're left with 71. And here, it matches up perfectly. So we're going to have y is going to be left with 1b and 1c. And again, we take the lowest median grade. So y, the lowest median grade, will again be a c. So x and y tie. So what we're going to have to do is remove one more c grade. But of course, if we do that, I'm not going to do the calculation again. You're going to see what happens if we remove one more. Then we'll have 70 C grades. And then y's grade, after removing one more after tie-breaking, y's median grade will be a B. So in the merged election, candidate Y is declared the winner. Whereas in each of these individual elections, candidate X was declared the winner. So this is an example of the multiple districts paradox. Now, those of you who have had a statistics course before, this should remind you of something that's a fallacy that's well known in the statistics literature called the Simpsons Paradox. So Simpsons Paradox works as follows. Suppose that you're at your university and you want to hire in the philosophy department and the mathematics department. Now, 13 men and 13 women apply for both jobs. So you go out and you tell the departments, whoever you hire, you want to end up with more women than men. So the percentages should be more women than men should be hired in each department. So mathematics goes out and do that. So of the 13 that apply to math, 5 are men and 8 are women. They hire 2 women and 1 man. That's a higher percentage of women. So the success rate for women is actually better. Philosophy does the same thing. There's 6 out of 8 of the men that applied were hired, and 4 out of the 5 women that applied were hired. So the success rate for the women is better in the philosophy department. However, when you look at the whole university, you have to add up, and here's the trick, you have to add up both the numerators and the denominators. So out of the 13 men that applied, 7 of them got hired, but out of the 13 women that applied, only 6 got hired. So overall, the success rate is better for men. So the multiple districts paradox you might really see as just a particular instance of Simpsons paradox. If you want to read more about Simpsons paradox, why it's puzzling, different resolutions to it, I recommend taking a look at this Stanford Encyclopedia of Philosophy article.